Hello everyone, welcome back to this series on solutions to previous year GATE chemical reaction engineering questions. This is part 5 of this series, which is continuation of part 4, wherein we looked at some of the questions from GATE 2022. In this part, we will be covering the remaining questions. So let's continue. An elementary irreversible gas phase reaction, A giving B plus C, is carried out at fixed temperature and pressure in two separate ideal reactors. The first one is a 10 meter cube PFR and the second one is 10 meter cube CSTR. If pure A is fed at 5 meter cube per hour to the PFR at 400 Kelvin, the conversion is 80%. If a mixture of 50 mole percent of A and 50 mole percent of an inert is fed at 5 meter cube per hour to the CSTR at 425 Kelvin, the conversion is again 80%. The universal gas constant R is 8.314 joules per mole Kelvin. And assuming Arrhenius rate law to be valid, estimate the activation energy for this reaction. So let's first note on the important information given. So we have a gas phase elementary reaction, A giving B plus C. So the order of this reaction will be 1. So we are having two cases. In case 1, we have pure A as the feed to the PFR, whose volume is 10 meter cube, and feed flow rate is 5 meter cube per hour, and conversion is 80%. The temperature in the reactor is 400 Kelvin. So let the rate constant for the reaction be K1 at this particular temperature. In case 2, we have 50 mole percent of A and 50 mole percent of inerts being fed to the CSTR. The volume of the CSTR, the feed flow rate and the conversion are same as that of case 1. However, temperature is different. Temperature is 425 Kelvin. So hence rate constant at this temperature will be K2. So we need to find the activation energy for this chemical reaction. Now, since Arrhenius rate law is given to be valid, if we are able to find the values of K1 and K2 at these temperatures using design expressions for PFR and CSTR, we can use the simplified form of Arrhenius rate law as shown here to find the activation energy. So now let's see the solution. So in case 1, we have pure A as the feed. Remember, this reaction is gas phase chemical reaction. So first we will have to find the volume fraction. So volume fraction for this case, let it be epsilon 1. So this will be equal to the difference of volumes of products and reactants divided by volume of reactants. So in case 1, the volume of reactants can be taken as 1 because pure A is being fed. So volume of products will be 2 units corresponding to B and C. So hence epsilon 1 will be 2 minus 1 by 1, that is 1. Further, the rate expression can be written as K1Ca, which can be further written as K1Ca naught into 1 minus Xa by 1 plus epsilon 1 Xa. Now we will use the design equation for PFR. Tau by Ca naught is equal to integral 0 to Xa1 dxa by minus Ra. So tau is basically the ratio of volume of PFR to that of the feed flow rate, which is 10 by 5. So we will substitute that as well as the rate expression that is shown here. So 10 by 5 into Ca naught is equal to integral 0 to 0.8 dxa by K1 Ca naught into 1 minus Xa by 1 plus Xa, because epsilon 1 was found to be 1. So further cancelling out Ca naught and taking K1 on the other side, we get K1 is equal to half integral 0 to 0.8 1 plus Xa by 1 minus Xa dxa. So this is one of the standard integrals. So we can solve this using the method of substitution. So after solving and substituting the limits, we get K1 is equal to 1.21 second inverse. So now let us look at the second case. In case 2, we have 50 mole percent of A and 50 mole percent of inerts as the feed. So considering this to be 2 units of reactants, volume fraction epsilon 2 will be 3 minus 2 by 2. So 3 is because we have 2 units of products that are being formed and 1 unit of inert that comes out unreacted. So hence epsilon 2 will be 0.5. Using the design expression for CSTR, we can simplify it as 10 by 5 into Ca0 is equal to Xa2 by K2 Ca0 into 1 minus Xa2 by 1 plus epsilon 2 Xa2. Epsilon is 0.5. So we can cancel out Ca0 and we can simplify by substituting all the values given in the question. And we find K2 as 2.80 second units. So hence we have found K1 and K2 at the two temperatures T1 and T2. So now we will take the ratio of these values. So K2 by K1 will be equal to 2.31. So now using the simplified Arrhenius rate law equation, we get ln 2.31 is equal to minus A by 8.314 into 1 by 425 minus 1 by 400. So on rearranging and simplifying, we get the activation energy as 47,334 joules per mole. So since we are required to give the activation energy in kilojoules per mole, so the answer will be 47.3 kilojoules per mole. So hence the right solution to this question is 47.3. Let's move on to the next question. An elementary irreversible liquid phase reaction 2P giving Q, where the rate constant K is 2 liters per mole minute, takes place in an isothermal non-ideal reactor. The E curve in a tracer experiment is shown in the figure below. Pure P with concentration 2 moles per liter is fed to the reactor. Using the segregated model, the percentage conversion of P at the exit of the reactor needs to be found out. So we have a second order reaction whose rate constant is 2 liters per mole minute. The initial concentration of the reactant is 2 moles per liter. We need to find the conversion at the exit of the non-ideal reactor. So let me just redraw this residence time distribution figure. It is in the form of a trapezium. Here we know two sides as 1 and 0.5 units. The other two sides are unknown. So let me rename it as Y and Z. So as we all know, the area under the residence time distribution will be equal to 1. Hence, area of this trapezium should be equal to 1. So area of trapezium is given by half into breadth into sum of the two parallel lengths. So half into 0.5 into 1 plus y will be equal to 1. So on solving this, we get y as 3 minute inverse. Now we know that for real reactors, Ca by Ca0 is equal to 0 integral 0 to infinity Ca by Ca0 element into E dt. So now here we need to find the value or the function of E in the particular time interval, that is 0 to 0.5. So if we observe the residence time distribution figure, E is a function of t between 0 to 0.5. So here I have depicted it as capital Z. So capital Z is actually a linear function of time. So hence E is varying from 0 to 0.5 as a function of time. So we'll have to first figure out the functional form of this Z and then substitute that in the Ca by Ca0 expression to get the final concentration of A. So as I already said, this is a linear form in T. So we know the endpoints of this particular line. So that is, so the coordinates of these endpoints of this line are 0, 1 and 0.5, 3. So using the 2-point formula of a straight line, we can find the straight line equation of this particular side of the trapezium. So we have y minus y1 is equal to y2 minus y1 by x2 minus x1 into x minus x1. So considering 0, 1 as x1, y1 and 0.5, 3 as x2, y2, and using the 2-point formula, we get E as 4t plus 1. So now we will have to use this functional form of T in the Ca by Ca0 expression. Further, since the reaction is second order reaction, the Ca by Ca0 element of this particular reaction will be 1 by 1 plus K Ca0 into T. This is the well-known result. So by substituting the values of K and Ca0, we get Ca by Ca0 element as 1 by 1 plus 4T. So now substituting the expression for Ca by Ca0 element and E in the given equation for the real reactors, we get Ca by Ca0 is equal to 0 to infinity 1 by 4T into EDT. So from the figure, it is obvious that beyond 0.5, the value of E will be 0. Hence, the integral can be reduced to 0 to 0.5. So integral 0 to 0.5, 1 by 1 plus 4T is found to be 1 plus 4T again into dt. So we can cancel out 1 plus 4T. We have a simple integral 0 to 0.5 dt. So this simplifies to be 0.5. Further substituting the value of Ca0, we get Ca as 1 moles per liter. So hence conversion will be 1 minus Ca by Ca0, which is equal to 1 minus 1 by 2, which is 0.5. So in terms of percentage, conversion will be 50%. So hence the right solution to this question is 50. So with that, we come to the end of part 5 of this series. So from parts 4 and 5, we have covered all the chemical reaction engineering questions from GATE 2022. In the next part, we will be looking at the chemical reaction engineering questions from GATE 2021. So if you like this video, please share and subscribe to this channel, and we will see you in the next part. Thank you.